Hello everyone, and welcome to a further discussion of torque, otherwise known as turning effect. Well, as we found in the last lab and afterwards, we can calculate an amount of torque or turning effect by taking the lever arm and multiplying it by the force. Of course, it's important to remember here that thus far we have defined the lever arm as the perpendicular distance from the axis of rotation to the point of application of the force. In other words, they're always perpendicular to one another. What if they aren't? What if the force and the distance from the axis of rotation, in fact, are the opposite of that? What if they're parallel? Well, let's think about a door. Let's say here's the axis of rotation, and what if you pull straight out on a door so that there is R? Let's look down on this so we can see it from a different viewpoint. There's our hinges, if you will. Right? There's our force straight out along the door, and there's R. Notice how they're now parallel to one another. Well, how much turning effect do you get if you pull straight out on a door or straight out on a wrench? Of course, you get none. You get no torque when the force acts through the axis of rotation. Okay, so when the force and the distance are parallel to one another, when the angle between them is 0, you get no torque. So you get a maximum amount of torque when R and F are perpendicular, and you get 0 torque when R and F are parallel. What trig function works that way? Let's see. Here's a random object rotating about a fixed axis. So here's the axis of rotation, and let's apply a force just at some random angle. There would be R. If we want to see exactly what the angle is between R and F, we have to draw the diagram a little differently. We have to pick up R and move it up there. When you draw two vectors tail to tail, that is the angle in between. Right? That would be the angle in between R and F. So let's define theta as the angle between R and F. Okay? R is the distance from the axis of rotation to the point of application of the force, and F is the force. Theta is the angle in between. Now, we could break this force up into perpendicular components. One of those components could be what we're going to call a radial component. It's at an angle theta to the force. Right? Notice that it is right along the same direction as the radius. But as we just talked about, a force which is parallel to the radius exerts no torque. It acts through the axis of rotation. You're pulling straight out on the object, you're not going to get it to turn at all. That means that the other component, which we're going to call F sub t for tangential component of the force, the part of the force that's perpendicular to the radius, if you will, is the entire cause of the torque. Right? So the entire torque is due to the tangential component of the force, and none of it is due to the radial component of the force. Now, sometimes this is drawn a little differently. We could draw the radial component there and the tangential component there, since they're all acting at that point. Okay, but this is the triangle we need to analyze, as if this one's over there. Okay. So what we're saying here is that we ought to be able to calculate torque by taking R times the tangential component of the force. But look at the triangle. F is the hypotenuse. There's the angle. F of t is the opposite side. So F of t is F sine theta. Rearrange, and we get a new definition for torque. The torque is R times F times the sine of theta, where theta is the angle between the force and the lever arm. Notice here, sine of theta. And think about what we were talking about earlier. When is the sine of theta a maximum? Right? Sine of theta is a maximum when theta is 90. So when they're perpendicular to one another. Sine of theta is 0 when theta is 0, when they're parallel to one another. So notice, sine is kind of the trig function that works here. If you're pulling parallel to R, you're pulling straight out or straight in, you're not going to get any turning effect. You're pulling or pushing perpendicular, and you get the maximum turning effect. So this is a more general version of torque. R times F times the sine of the angle in between. Now here's R again, and we could look at this slightly differently. Okay? Instead of breaking F up into components, let's break R up into components. Right? There's the angle in between. There is the line of action of the force, the extension of the force. Right? And if I drop this across, Notice that this is the part of R that is perpendicular to the force. Everybody with me there? R perpendicular is the part of R that's perpendicular to the force. And notice, if this is theta, this is theta. So from our original definition that we got out of the last lab, torque is R perpendicular times F. But look at the right triangle here. Right? R is the hypotenuse, theta is the angle, R perpendicular is the opposite side, so R perpendicular could be rewritten as R sine theta. Plug that in, rearrange, and again we see that torque can more generally be written as RF sine theta. So we basically have three ways now of calculating torques. This is the way we saw in the lab. Torque is R perpendicular times F. So it's the perpendicular part of R times F. Or as we just saw a moment ago, it's R times the tangential part of the force, the perpendicular part of the force. Or, more generically, it's R times F times the sine of the angle in between. And again, to see the angle in between, you really need to draw the vectors tail to tail. So I hope you see here that there's three different ways to calculate torque. Why do we have three different ways? Really, the geometry of a particular situation is going to guide us in a direction here. This is the most generic version, but sometimes it's not easiest. If we think of the lab, for example, this was the easiest way to do it because we could measure this one really easily. Sometimes we might be able to measure the tangential component more easily. It's just going to depend on the geometry of a particular situation. So I hope you enjoyed this expansion of the idea of torque.